Good afternoon, everyone, and welcome to the EOL seminar series. To kick off our first seminar of 2021, we have a triple whammy special, a joint EOL, M-Cubed, and Sizzle seminar. The special guest whose work overlaps with the three NCAR labs is Hristo Chipilski, a PhD candidate from the University of Oklahoma. His advisors are Zhuguang Wang and Dave Parsons, whom you may know from his tenure at EOL. Hristo obtained his master's in meteorology at the University of Reading in the UK, where his thesis focused on theoretical aspects of data assimilation of moisture at convective scales. He will be defending his PhD this year at the School of Meteorology at the University of Oklahoma, where he is a member of the Multiscale Data Assimilation and Predictability Laboratory. Part of his thesis includes using Pecan campaign observations in assimilation studies with a focus on nocturnal mesoscale convective systems, which is a topic of today's seminar. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Do not be alarmed if you do not see your question on the Slido window, because we are archiving all questions that will be revealed during the Q&A portion of the talk at the end of this presentation. Hristo Chipilski, we welcome you to NCAR, and the virtual stage is yours.
Thank you for this introduction and welcome everyone. I hope you all had a wonderful holiday season and are looking for one more positive year ahead. Thank you for attending this virtual seminar today. We'll be talking about the assimilation of ground-based remote sensing profilers. More of a broad aspect, I'll try to cover a couple of interesting topics related to the motivation, forecast benefits, and challenges ahead. And before I start, I would like to specially acknowledge my advisors, Dr. Zhuguang Wang, Dave Parsons, as well as my former advisor from the University of Reading, Ross Bannister, and many other colleagues who have contributed to the contents of this talk. So, as you may have gathered from the outline of my seminar, today we'll be covering three distinct topics. The first one will be me trying to motivate the importance of ground-based remote sensing instruments, both for the physical understanding of Earth system processes, as well as for improving the predictive capabilities of numerical weather prediction models. Then, after this broader context has been set up, I'll try to talk about the forecast benefits from these instruments. And here I'll use some of my Pecan research from the PhD to review in what ways these instruments can be beneficial for one specific application. This is the application of board-driven nocturnal convection. And finally, we'll touch a little bit about the assimilation challenges in the assimilation of moisture retrieved quantities. And in the sake of time here, I would like to focus particularly on some of the non-Gaussian aspects of moisture data assimilation. Let's go to the first part of the talk then, the motivation. Undoubtedly, in the last years, our community has started to expand beyond its traditional focus on the atmosphere and atmospheric processes to a more encompassing view involving the whole Earth system. And I think you would agree with me that to a large extent, this shift into other aspects and components of the Earth system is driven by the increasing awareness that in order to adequately understand the atmospheric processes, we also need to understand how those are impacted and influenced by processes in other components of the Earth system. And here I'm presenting you this sample schematic from the IPCC report in 2007, just to hint at the enormous complexity of the Earth system processes, but also the many different ways in these processes can interact with the atmosphere. Now, in order to capture this complexity in the Earth system, we need to have a proper observing system. And thanks to progress in science and technology, we have already made significant efforts in this direction. So here, for example, you're seeing a schematic of the global observing system. And we can see this large variety of instruments that are comprising the so-called global observing system. A lot of instruments that are able to sample many of the processes on the Earth. And what is nice, one of the nice features about this global observing system is that it is a dynamic environment in which we can add new instruments in a hope to further advance our understanding of the Earth system processes and its other components. Despite this variety, though, in the instrument types and observing capabilities, in the last decade and even further back in time, there has been a couple of reports from the National Research Council that have concluded the existence of an observation gap in the planetary boundary layer, which is the lowest portion of our atmosphere. And these reports have concluded that one of the reasons for the existing gap is that we don't have sufficient coverage in this lowest portion of the atmosphere. This is one of the reasons. So let's take, for example, the surface network. We have started to expand the number of observations near the surface ever since the Second World War, when observations were critical for making weather forecasts and for assisting the military operations at the time. But the problem with surface observations is that they're made mostly of in-situ instruments. And because of that, we can only sample the lowest couple of meters above the surface. You may ask, what about satellite instruments? We have a global coverage of them, and we have unprecedented numbers of observations, especially now in this new era of satellite instruments. However, when it gets to boundary layer processes, the resolution of these instruments is simply not sufficient to capture the processes there. And there are further complications as well. At certain wavelengths, for example, here at the infrared, the observations cannot penetrate the clouds, and therefore they're of limited use for the boundary layer processes. And here we're not saying that there are no observations at all in the boundary layer. We have radiosondes. This is the golden standard for upper air measurements. But the problem with radiosondes is that we only take them twice per day, operationally, one at 0 UTC as well as at 12 UTC. And because of that, we don't have enough data to describe the processes well. We also have some occasional observations from commercial aircraft, for example, through the Atmospheric Meteorological Data Relay Program. But the problem with these commercial aircraft observations is that they're not reliable, and we cannot use them to advance our scientific understanding and prediction of the Earth system as a result. This insufficient coverage is also compounded by another problem that here I would like to illustrate by using this famous diagram from the study of Orlansky in 1975, who characterized atmospheric processes as a function of their characteristic horizontal and temporal scales. And I would like you to focus on two key facts here. The first one is that a lot of the processes that are depicted in this diagram are originating from the boundary layer, or in other words, their dynamics is intricately related to what happens down in this lowest portion of the atmosphere. Take, for example, turbulence, convection, tornadoes, disturbances in the mountains. All of these have dynamics coupled to the boundary layer processes. But the second fact I would like you to note here is that a lot of these boundary layer processes are located in the lower left portion of this diagram. And what this means is that their scales are smaller than the synoptic scales that our current operational networks are designed for. So in other words, the insufficient coverage of boundary layer observations is compounded by the smaller spatiotemporal characteristics of the processes in the boundary layer. And therefore, we further exacerbate the existing boundary layer gap. Now, what can we do to close this gap? there have been a lot of recommendations and advice to increase the number of observations ever since the beginning of the 21st century. But more coordinated efforts really arrived first in 2009 with this National Research Council report from 2009, the first in the series that I mentioned a couple of slides ago. And the recommendation for confronting the boundary layer gap that we explained was to deploy this nationwide network of ground-based remote sensing profilers, specifically comprised of LiDARs and radio wind profilers, which, if we do the math, take the area of the United States, this would correspond roughly to 125-kilometer horizontal spacing. Some of you may ask the question, but this is still not sufficient to represent many of the processes that we described in the previous Orlansky diagram. I would agree with this statement. However, the justification that went in this initial report was that such a horizontal spacing of 125 kilometers is still an important first effort to improve the skill of numerical weather prediction models. And the reason for this is that numerical weather prediction models use data assimilation to create their initial conditions. And data assimilation is a statistical process in which we combine observations together with a model background in order to fill in some of the remaining observation gaps. Further reports confirmed some of these recommendations. And here I would like to just maybe point out this decadal survey from 2018. The reason why I wanted to point it out is because it arrived at these very specific recommendations for best practices of observing boundary layer variables. For example, here you can see that to ideally do that, we would need a horizontal spacing of about 20 kilometers, temporal frequency of 2-3 hours, vertical resolution of 200 meters, and uncertainties that are pretty comparable with some of the radio sound uncertainties that we have right now. So after these recommendations, then, of course, a lot of studies started to study the feasibility of such a nationwide network of profilers. And here in the remaining 2 slides of this first segment of the talk, I would like to describe some of the historical context so that we put ourselves in a good position for the second part of the presentation. So, of course, showing these NWP impacts in idealized experiments is the way to really justify the operational deployment of such an observation network. And historically speaking, some of the first efforts were mostly to do with kinematic profilers. The reason for this is that kinematic profilers, the precision and the accuracy of these instruments was more superior to their counterpart thermodynamic profilers. And that's why the first studies were focusing on this particular type of profilers. And here you see a picture of the radio wind profiler, which was one of the first instruments to be systematically tested in many studies. Here I've cited the fundamental study of Kuo et al. 1987, where we showed positive impacts from radio wind profilers in an experimental setting, and many other subsequent studies. And as a result of these positive impacts, this was one example where we started to assimilate radio wind profilers in an operational setting, including at centers such as the European Center for Mid-Range Forecast, as well as the National Center for Environmental Prediction here in the United States. More recently, efforts have also tried to assimilate new type of kinematic profilers, those coming from the Doppler wind LiDAR, and also have shown many positive impact results. The reason why the Doppler wind LiDAR is such a desirable instrument in some of these new studies is because it can provide unprecedented observations of near storm environments. For example, if you have a thunderstorm, that thunderstorm is typically observed pretty well by weather radars, but the Doppler wind LiDAR will fill in the gaps and provide wind information in the environment around the storm. And thereby, we should expect the analysis and the forecast of these storms to be further improved. And as I mentioned, thermodynamic profilers, the technology matured a little bit later, but now it's a very exciting area of research. So here I would like to review a couple of important results that have been shown so far. Like satellite sensors, thermodynamic profilers are divided into active and passive sensors. And in terms of NWP impacts, an example of an active sensor that has been quite heavily utilized in previous forecast experiments. This is the LIDAR atmosphere sensing experiment, the LACE. There is a logo of it here on the lower left part of the slide. This is a differential absorption LIDAR. It retrieves moisture, and we have seen a lot of impact for high impact weather applications, including deep moist convection and hurricanes. Now, I realize that the LACE is an airborne instrument, and this is my talk is for ground-based profilers, but I wanted to give this as an example because it really has been used quite heavily in the NWP world. But more recently, there was a ground-based style that is now under active development. Here in NCAR, in EOL lab, there have been a lot of promising results for convective applications. So which shows that both types of instruments can be used maybe to even complement each other in future forecasting experiments. In terms of passive profilers, I think the canonical example in our NWP community, this is the atmospheric emitted radiance interferometer. This is an instrument which one of the benefits that makes it so maybe preferable to these previous two instruments in some respects is that it's able to simultaneously retrieve both temperature and humidity. And there have been a lot of studies recently with the ARRI instruments too that have shown positive impacts for a range of applications, ranging from convective initiation on the small scales to large extratropical lows. Now, the second segment of the talk, we'll continue with the important topic of forecast impacts, but now we will be restricting our attention to the specific application of Bohr-driven nocturnal convection, and I'll try to justify why this application is suitable for showing the forecast impacts of profilers. So for those of you that may not be so familiar with atmospheric bores, here I've tried to give you an overview, 101 introduction to what they look like and how they form. For that purpose, I have used this diagram from Kage et al. 2017. And if you focus on panels A and B, you'd see that atmospheric bores are mesoscale phenomena that form when you have a stable layer interacting with an obstacle, typically in the form of a density current or a cold pool generated by a thunderstorm. And as a result of this interaction, if the conditions are favorable, we're going to see a hydraulic response in the environment. And later on, this hydraulic response will propagate away from the density current, and typically we'll see the generation of wave activity in the wake of the bore. So the more relevant question here is, why do they choose Bohr-driven convection to study the forecast impacts of ground-based instruments? Two reasons. The first reason is that I wanted to study these impacts with respect to a new type of convective application that is also highly challenging. If you remember, a lot of the previous studies, there were convective impacts being studied, but they were focusing on the daytime convection. By contrast, you see by the name, Bohr-driven nocturnal convection occurs during the night, and previous studies have shown that the predictive skill of numerical weather prediction models are fairly poor with respect to nocturnal convective systems. So in other words, if we're able to show that the assimilation of ground-based remote sensing profilers is a positive impact on these highly challenging convective modes, I think this would be highly valuable and would be a justification for their operational procurement in the future. The second reason why I chose this application is slightly connected to some of the discussion we had in the first part of the talk, and namely that Bohr during convection is controlled by many processes whose origin is in the boundary layer. Examples of those include the strength of a nocturnal inversion, we have the structure of the low-level jet, the static stability, and so on. I already justified in the first part of the talk that all of these processes are very poorly observed with current operational networks. So therefore, I think we can make here the hypothesis that by improving these processes through the assimilation of ground-based remote sensing profilers, we will be hopefully able to see positive downstream impacts with respect to forecasting this challenging phenomenon. So I'll try to prove this hypothesis through a case study approach, and I'll try to convince you of this, the result of this hypothesis by the end of this segment. Here, the case study we'll be using is the 6th of July, 2015, Pecan case study, which is one of the most well-observed case studies, one of the reasons why I picked it. You can see that throughout the evolution, throughout the mission, we had a lot of convective storms that throughout the night merged together to form one large mesoscale convective system. And with the stabilization of the nocturnal boundary layer and the setup of a low-level jet, we observed these two episodes of Bohr-initiated convection, one in panel D and one in panel G. And so this new convection that developed as a result of the lifting of parcels by the Bohr helped maintain the system throughout the night and increased its longevity. Now, for the sake of time, in this segment, I will be focusing on this first episode of Bohr-initiated convection. And here I provided this radar image so that you can get a more detailed sense for where the convective cells originated, as well as how the Bohr propagated away from the mesoscale system. Here, my focus will be, can we predict this first episode of Bohr-initiated convection without the assimilation of profiling instruments? And after we assimilate these profiling instruments, how does this change the forecast? Let's answer these questions one at a time. First, though, I would like to show you, just to get a spatial sense for where things were located throughout this mission, two figures. Here I have plotted the location of the assimilated Pecan observations in all of these markers. And also I have overlaid the radar images from the MRMS dataset, first at 3 UTC, which you'd see corresponds with my forecast initialization time, and 2 hours later at the start of the Bohr-initiated convection event that we'll be focusing on. I would like you to note that these Pecan observations were fairly inhomogeneous in space. So we had this one fixed site in the southern Nebraska, as well as observations in the southeastern portion of South Dakota. And the second point I would like to make is that there was the Bohr convection that we'll be focusing on developed upstream of the fixed site in the southern Nebraska. So most of the impacts that we'll be commenting here will be coming from this fixed site here. And note this couple of markers here with the maroon color. These will be some of the aircraft measurements with which you'd see the Bohr observed and with respect to which we will verify our forecasts. Couple of words about my experimental design. I would just like to focus on this red segment here, which is where we'll assimilate the Pecan observations. You can see here that the bulk of the assimilation happens on this high resolution 1 kilometer domain, whose position is shown in the lower left figure. The data assimilation frequency is every 10 minutes. And here we'll be assimilating a couple of different data types, including the conventional data from the operational and DAS data stream. We'll be also adding radar observations. So these two first types form the baseline experiment. And then we'll be adding also Pecan profilers, either ARI to form the ARI experiment or radio wind profiler to form the wind profiling experiment. The reason why I've chosen these two experiments here is for the sake of time, but also to emphasize the differences in a simulating thermodynamic profiler with the airy experiment and a kinematic profiler with the radio wind profiler. These are the aircraft measurements that I talked about in 2 slides ago, with the maroon color. These Bohr observations are coming from the so-called compact Raman LiDAR instrument. This is another example for an active remote sensing instrument. And here you see height and time resolved profiles of mixing ratio. And I have annotated the subjectively determined height of the stable boundary layer with this black contour. You can see the delineation of the Bohr by the semi-permanent rising of the stable boundary layer. But also you can see the two waves that were formed on the subcritical region of the Bohr behind the hydraulic jump. So now let's see first how the forecast predicted this Bohr. Here we see the model equivalent of the King Air aircraft cross sections, but for the from the ensemble forecast fields. The blue line here denotes the height of the stable boundary layer, and we can see that there is a semi-permanent lifting of the stable boundary layer height. Therefore, we can conclude that the control experiment is correctly simulating a Bohr. However, if we compare with the observed Bohr here in the magenta line, we see that there is this underestimation of the Bohr height on the order of 3 to 350 meters. That was the problem in this forecast simulation. So now the question is, what happens if we simulate thermodynamic or kinematic profilers? These you see in the bottom 2 plots. First, the airy and then the wind prof experiment. Comparing with the baseline solution here in the dashed black, we see that the airy experiment predicts a Bohr by the semi-permanent displacement of the stable boundary layer height, but it improves the prediction of the Bohr height a little bit, closer to the LiDAR observations. And quite the opposite for the wind prof experiment, we see the slight decrease in the Bohr height. So opposite effects coming from these 2 instruments. What about the convection, this first episode of Bohr convection that I wanted to talk about in this segment? Now that we've explained the Bohr forecast, we'll also like to see to what extent the simulated Bohrs were able to produce the this first episode of convection. To answer this question objectively, here I'll be using the neighborhood ensemble probability fields in color shading of threshold being 35 dBz. And I'll be comparing this to the observed 35 dBz contour of MRMS radar data, here shown in the black contours. And let's first focus on the first row. This is the control experiment. And we see that while there is some increase in the probabilities toward the beginning of the forecast, overall, throughout this 30-minute period, the control forecast can't really depict the increase of the probabilities along the first episode of Bohr convection. On the opposite, though, we see that if we simulate airy, there is a significant increase. So these are the neighborhood ensemble probability differences between the airy and the baseline. And we see this significant increase in the probabilities. And we can even see that the experiment is able to correctly depict some of the storm morphology by separating the convective development on the southern cell and this northern cell. On the opposite, the wind prof experiment decreases the convective probabilities and further degrades the forecast results. So in that sense, the positive impacts from the airy and the negative impacts from the wind prof are repeating what we observed on the previous slide with respect to the Bohr forecasts. So clearly there is some connection between these 2 results. And I would like to explain this connection in the last 2 slides of this segment. To explain this connection, I will be showing you cross sections one more time of the 3 experiments, but instead of drawing them in vicinity of the King Air observations, in these 3 cross sections, I have drawn next to the region of Bohr convection. Again, you see the same sequence of baseline, airy, and wind prof. Similar to before, we observed that the baseline underestimates the bore height at this new location. The airy increases the bore height, and the wind prof decreases the bore height. So same impacts as before, but what is new in this set of cross sections is the tremendously increase in the moisture field ahead of the airy simulated bore. So now the question is, where did this increase in moisture come from? To answer this question, I'll play you an animation which shows the mixing ratio differences at water vapor mixing ratio at 850 millibars, here between the airy and the baseline experiments. And you can see here that we're tracing it from the analysis time all the way to the forecast. We see that the assimilation of airy data, which is from the FP4 site, leads to these positive moisture differences, which are propagated and vectored to the north throughout the assimilation cycle. And then later on, when we hit the bore convection, they start to propagate with the bore towards the east-southeast. So in other words, what we can conclude here is that the better bore forecasts in the airy experiment are really caused by the simultaneous corrections in two main components. So the first one is the ambient moisture environment. By increasing the amount of elevated moisture ahead of the bore, we are destabilizing the layer in this elevated air, making it easier for convection to develop. And on the other hand, by increasing the height of the bore, we're increasing the amount of mechanical lifting that parcels will undergo as they approach the bore. Both of these impacts help the convection to initiate in the environment, and that's why we see the improvements in the airy forecasts. We also prove with this case study an earlier hypothesis that the assimilation of certain profiling instruments can improve the bore convection forecasts by improving several aspects in the nocturnal boundary layer environment. And having talked about the importance of moisture in this second section, I would like to now move on to the last segment, where I'll focus on some of the challenges in assimilating moisture variables in future data simulation systems. And in the sake of time, again, I'll focus on the non-Gaussian aspects of moisture variables so that we can have a more in-depth discussion. Non-Gaussian distributions in data simulation are not ideal because most, if not all, operational data simulation systems are built on the Gaussian assumption. But unfortunately for us, moisture variables are especially susceptible to non-Gaussian effects. And there are two reasons for that. The first reason is that moisture variables have physical bounds. Take, for example, relative humidity. We know that relative humidity is bounded by 0 and 100%. So now, if we draw the error distributions of relative humidity as a function of the relative humidity value itself, like I've done here in this adapted figure from Colm et al. 2007, you'd see that in the middle range, when relative humidity is about 50%, the error distributions are approximately Gaussian. But as you move closer to the bounds, the error distributions become skewed in order for these bounds to be observed. And so what is more important here for us is that we know most of the interesting weather happens when relative humidities are closer to 100%, because you have dynamical effects such as phase changes of the atmospheric water, release of latent heat, and so on. And therefore, we know that the non-Gaussian effects will become important for the moisture analysis quality and the subsequent moisture forecasts because of these dynamical processes happening near the bounds. The second reason for observing non-Gaussian distributions for moisture variables is connected to the generally nonlinear dynamics of moisture. And examples of these, as I already mentioned, are phase changes of water vapor, of atmospheric water, as well as more generally, the turbulence of moist convective flows. When I want to draw a connection between nonlinearity and non-Gaussianity, I really usually like to refer to this excellent figure from the review paper of Bouquet et al. 2010, who shows how if we start from initially Gaussian distributions, then under the influence of the highly nonlinear Lorentz 63 model, the Gaussian distributions will gradually start to deform and to deviate from the original approximations. And one observation we can make here is that for short enough times, when the model doesn't integrate for much longer, the distributions remain approximately Gaussian. But as we go further into the forecast, the deviations from Gaussian distributions increase. That tells us that one way to suppress detrimental impact of nonlinearity in our dynamical system is if we decrease the time periods between subsequent analysis times. But the problem with this approach is that we may introduce a lot of model imbalances, which will create other problems we need to solve in other ways. So perhaps it's not the best way to go in the grand scheme of things. There have been other methods, though, that we have tried historically to address these moisture non-Gaussian effects. And going back earlier, one of the first ways to look at this problem was to choose a suitable moisture analysis variable. And what is the reasoning behind that? There are a lot of moisture variables. You have specific humidity, relative humidity, dew point. All of these variables describe the same moisture properties of the atmosphere, but they have different statistical properties. Some of those will have statistical properties that are more suitable for operational data simulation algorithms. So can we exploit this fact? Well, first, that fact was exploited systematically for the first time in the study of Dian de Silva in 2003, who compared the statistical properties of many different moisture variables. And one of the interesting conclusions that came from this study was that relative humidity is a better analysis variable than specific humidity, despite its doubly bounded character. So that is somewhat of a surprising result. However, we need to keep in mind that these results refer to a global NWP model on one hand. It's not clear whether relative humidity or any other moisture analysis variable will also have the same desirable statistical properties at the convection permitting resolutions. And also, when we say better statistical properties, in this paper, these were defined to go beyond the simple notion of a Gaussian approximation, and they actually included more multivariate aspects of the data simulation problem, including the degree of spatial inhomogeneity, as well as the amount of cross-variable correlations. However, even if the world is not ideal, we all know that, perhaps even, especially this year, we were faced with this realization even more so. But even if we're able to choose well, in a judicial way, a good analysis variable for the moisture, we need to realize that there will be a lot of instances when the statistical assumptions will still not fit traditional data simulation methods. There will be cases and situations, whether situations in which the traditional Gaussian assumptions will still not hold, however good the variable is. So now the question is, what has been done to address this problem? A practical solution has been applied, starting from 2003, and this practical solution has worked pretty well for geophysical applications and many other areas of applied science, and it is to apply nonlinear transformation to the original moisture analysis variables, such that the transformed moisture variable have statistical properties that are closer to a Gaussian approximation. To illustrate this, I would like to give you a simple example with specific humidity. Specific humidity is a non-negative quantity, and that's why we typically can model it as a log normal random variable. Now, using basic definitions from probability theory, we know that if we take the logarithm function of a log normally distributed random variable, then the result, which I denoted here by big Q, will be a Gaussian random variable. And this would appear to better suit current operational data simulation schemes. And so what is done in this practical approach with a nonlinear transformation is that we keep the analysis system as is. That is, we keep the analysis equations the same. They're the same Gaussian-based equations. However, instead of doing the analysis with respect to Q, we run the data simulation algorithm with respect to big Q. And then, after the analysis is obtained, we take the inverse of the nonlinear transformation. In the case of a logarithm function, this is the exponential function, to recover the specific humidity analysis fields. And the desirable feature behind this approach is that if we have an ensemble component to our data simulation system, then this simple idea of a logarithm transformation can be extended to any arbitrary starting distribution. Could be log normal, gamma, inverse gamma. It doesn't matter. The transformed ensemble will be, the transformed sample will be approximately distributed according to a Gaussian law. However, despite its practicality, there's now piling evidence that such nonlinear transformations do not provide the optimal solution of our data simulation problem. And I would hope to justify this a little bit in the next couple of slides and provide my own vision for where data simulation research should be going in this particular direction. So how can we further improve the moisture analysis, and how can we ultimately make better use of moisture, retrieve moisture quantities, and in general remove sensing information that exhibits such non-Gaussian effects? So my personal take on this question is that we should go back to first principles in order to derive completely new data simulation algorithms in which the non-Gaussian character of moisture variables is treated in a mathematically rigorous manner. And luckily for us, there has been progress in this direction that we can build upon. And here, I would like to provide two specific examples to motivate the benefits from such an approach and to stimulate further efforts in this area of research. As you know, data simulation, typically like in geophysical applications in particular, algorithms are divided into variational and ensemble algorithms. Here, I would like to talk about the variational part of these algorithms. For those of you who are familiar with the variational data simulation problem, a central object in this estimation procedure is a cost function, which we wish to minimize in order to obtain an analysis solution. And Gaussian-based cost functions have the nice property that they're quadratic, they're convex, therefore their minimization through numerical algorithms is pretty straightforward. However, this is not what we want for moisture variables. We really want to have new cost functions that can accommodate for non-Gaussian error distributions in a mathematically rigorous way. And progress in this direction has dates all the way back to 2006. This idea has been proposed already. This seminal paper of Fletcher and Zupansky in 2006, who developed a new cost function which minimizes errors with respect to log normally distributed errors. And more recently, a new cost function was also introduced, which has a combination of Gaussian and log normal random variables in the state vector. And this mixed approach is particularly suitable for thermodynamic retrievals. And here I've borrowed this figure from the Quiller et al. 2016 study to show you an example for a retrieval accuracy with respect to the satellite AMSU-B instrument. And here, what I'm showing is the retrieval accuracy, which is the best the closer you are to zero, for the mixed approach with Gaussian and log normal variables, cost function that accommodates for this mixture of random variables, this naive log normal transformation approach in which we still work with a quadratic cost function and do not change the original cost function, and the original Gaussian cost function in which we simply analyze the state as it is. And what we notice here in this particular set of experiments is that the mixed approach, which is with the solid black curve, provides the best solution. The worst solution is by the Gaussian approach, which is in the upper curve, and the transformed approach provides an intermediate quality solution. So there is some benefit to such a transformation approach, but it cannot beat the rigorously derived mixed approach where we have completely reformulated the underlying cost function we wish to minimize. And this type of idea of going back to first principles to derive new algorithms that treat these non-Gaussian distributions in a theoretically rigorous way also can be applied with an equal success to ensemble-based algorithms. And here I'd like to give another example with the gamma inverse gamma ensemble common filter of Craig Bishop that was introduced for the first time in 2016, where we rigorously accommodate for gamma and inverse gamma probability densities. Now, these densities are especially suitable for the estimation or retrieval for atmospheric water variables such as rainfall, cloud parameters, and so on. And in a follow-up study that Craig did in 2019, I'm showing this figure from his paper where he compared the accuracy of his Dickey-Kiev filter to other ensemble filters, and we see the same result as in the previous slide. The worst solution is by the Gaussian-based methods, these upper three curves. We have we improve the solution with the naively applied logarithm approach with the sine curve, but really the best solution is given by the Dickey-Kiev filter, in which these uncertainties are treated in a rigorous way. So a new analysis equations have been derived, and they give us a better solution because this is the mathematically correct way to do it. And I would like to close this last section with an example that is closer to the type of work being done at NCAR and EOL with the MPD instrument. And this slide here was inspired by an interesting discussion that I had with Matt Heyman from EOL, who works on the retrieval of the absolute humidity for these instruments. So the problem here can be summarized as follows. We have photons hitting the LiDAR sensor, and this is what we observe. But then based on these observations, we want to reconstruct the absolute humidity field. So the reason why I was interested in this problem throughout this discussion with Matt is because this represents an excellent example of a non-Gaussian estimation problem. This is because the number of photons hitting the LiDAR sensor can be best modeled as a Poisson stochastic process instead of a Gaussian stochastic process. These counts, like in many other natural processes like radioactive decay, web serving queuing, these counting processes require a Poisson model. And the way that the retrievals work right now is that we maximize the corresponding Poisson likelihood. And the practical consequences of this substitution of a Gaussian to a Poisson likelihood is that we change our cost function from a quadratic to a non-quadratic type and potentially non-convex cost function, which makes the retrieval problem more difficult and requires some special considerations. For example, you'd need to carefully choose your regularization terms, penalty terms, and so on. Now, instead of doing that, there is another way in which we can assimilate the MPD data, which is to directly assimilate the raw photon counts with such a theoretically derived non-Gaussian data simulation method. And luckily for us, such a method has been, someone already did the work to create a method that is suitable for the MPD instrument, and this is the so-called ensemble Poisson gamma filter. It's similar to the gamma inverse gamma filter. It's actually derived in exactly the same way mathematically, but right now it has been used in the real-time monitoring of crime data in urban areas, not in geophysical applications. But the reason why the EMPGF would be suitable for the MPD data is because it incorporates Poisson likelihoods, which is exactly what we need in order to assimilate the photon counts coming from the MPD instrument. And there are a couple of advantages of this approach compared to the retrieval process. Instead of assimilating retrievals by directly assimilating these raw photon counts, We will avoid extra computations that are related to the retrieval process, but also by avoiding this retrieval process, I think we have a more straightforward way to quantify the uncertainties in the observation process. The choice of a noise model, the choice of a likelihood, this becomes more straightforward. But perhaps most importantly, we're able to further constrain the absolute humidity field, not only with the observed number of photon counts hitting the LiDAR sensor, but now also using a dynamical prior, which in our case, in the case of the ensemble Poisson gamma filter, would come from the ensemble forecasts that are run as part of the numerical weather prediction model. And just to summarize, this is the final slide here, the key points from the 3 parts of the talk. In the first part, I tried to motivate the importance of ground-based remote sensing profilers for closing the boundary layer observing gap that is currently existing, for understanding better Earth system processes, for improving the predictive capabilities of current models. Then in part 2, you can think of it as a specific instance of part 1. I try to show the forecast benefits of a specific type of instruments for the specific type of board-driven nocturnal convection application. And in this part, we saw that moisture plays a very important role in improving the forecast in this particular case. And inspired by these results in part 2, in part 3, I tried to talk a little bit about the outstanding challenges in assimilating retrieved moisture quantities. And with the 2 examples from the variational and ensemble data simulation worlds, I'll hope to further stimulate future efforts into this important area of theoretical data simulation research. And with that, I would like to close this slide and give you an opportunity to ask your questions. Thank you very much for your attention.
Great. Thank you, Hristo, for a wonderful presentation, motivating us to keep our profiling measurement systems going. A very nice introduction to the various profilers in use, and a crash course in non-Gaussian methods. We have time for questions. Again, please use the Slido interface, which is below the presentation screen. And I believe we have a few questions coming up. We have a question from Belai. How do you square this area improvement via moisture with Weckworth et al. Work in Pecan that found ARI may have issues in moisture in elevated levels?
That's an excellent question. Thank you for that. The moisture, as I hinted out in the second part and going toward the third part, we saw that the ARI instrument has this temporal frequency of, high temporal frequency of adding moisture instruments. However, right now, one problem with the ARI instrument is that there is just too much noise. And when we're simulating this noisy data, we really need to make sure that they're simulated in with a right way of quantifying the observation uncertainty. And certainly, there is a lot of scope for improvement. I think quantifying this observation uncertainty is one way to go about it, but also rigorously treating the moisture statistical characteristics is another important area that I try to emphasize in this third part. Also, I would like to say, even though there are problems with moisture retrievals, data simulation should be designed to take care of these problems, because it is an optimal statistical procedure in which, if we specify the uncertainties in an optimal way, then we should get an optimal solution as well, given that the dynamical process and the observation process are accurately modeled. So even though these instruments have deficiencies, if these deficiencies are modeled in the right way, then we should be able to see forecast improvements.
Thanks for that question. Thanks for the answer. I think we have another question. We have a question from Ben Pickering. Great talk, Hristo, thanks. It seems that vertical wind profilers may have some competition from UAS drones. What are your thoughts on the two methods for operational NWP benefits? And will any of the non-Gaussian DA issues change or improve with an in situ UAS profiler versus a remote sensing profiler?
Thank you, Ben, for this question. I actually have a couple of thoughts to share on this topic. I'll share my screen just to illustrate this. Let's go here. All right, so when it comes to confronting the boundary layer gap, Ben is right that, and I know he's been working on UOS like many other people here at the School of Meteorology in OU. Certainly, profiling instruments are one way to solve the problem, but there are other competing observing platforms. On one hand, you have satellites that are starting to have better and better resolutions through the infrared sounders and so on. Other instruments that may have a fine precision measurements of the boundary layer. But one other observing platform that is starting to gain traction, this is the US. People usually think of them as drones in which you have sensors. So here, I would like you to refer you to a recently published paper by Tyler Bell from my department, who specifically talked about this problem of the benefits and the disadvantages of these two different observing platforms. They have each their own benefits and disadvantages. For example, in terms of network considerations, we know that UOSs are considerably cheaper, so that makes them very desirable for NWP. But what really makes them preferable perhaps to profiling instruments is, I think, the adaptability in the measurement location. You may have heard about a lot of previous efforts with respect to targeted observations. So for example, hurricane is one application here. When you have targeted observations, we typically sample this portion of the state, which is especially prone to development of errors further down in the forecast. So the ability to move measurements in different parts of the model domain could be particularly useful going forward. And in terms of observing capabilities, they both have significant improvements compared to the benchmark radiosound. But I think in terms of vertical profiling characteristic, this is where perhaps there's further scope for improvement in terms of UAS technology, because even though we have truly vertical profiles with them, they still do not provide these truly instantaneous vertical profiles. There's some time delay going from the surface to the top of the boundary layer. So I think it will be very exciting to see the development of these two platforms. And what will be more exciting to me to see from the observational folks out there is to see ways in which different observing platforms like UAS and profiling technology can be optimally combined together to fill in these remaining gaps in our coverage.
Great, thanks for that question. I believe we have several more questions coming up for you, Hristo. We have one from Carol Costanza. Why do you think the addition of the wind profiler's observations didn't improve the accuracy of the forecast model in part 2?
Yes, so wind profilers, you saw that from the first part of my talk. There were the choice of instruments from earlier studies for NWP forecast impacts. However, in our particular case, and in other case studies that have come up in the literature from my group and from other groups, we have observed, unfortunately, some negative impacts. And I think one reason for that is that the data simulation algorithms cannot reliably extrapolate the wind information to other variables through the so-called cross-variable correlations. So, and to a large extent, this again justifies and further emphasizes my point that we need to have further advances in theory in data simulation to optimally extrapolate these moisture observations, the moisture state variables, to other variables, you know? So if we're not able to optimally extrapolate the wind information to the moisture part of the state, then we'll see negative forecast impacts in many cases. In this particular case, the negative forecasts were due to, I guess, the inability of the wind profiler to see that the increase in the low-level jet speed for my case study should also correspond with an increase in moisture. So it wasn't able to simultaneously measure both of these processes happening at the same time. And this is one other component of the profiling instruments that has to be accounted for in the future. They become especially, I think that this synergy between thermodynamic and kinematic profilers has to be further improved on in future studies so that we can optimally get this full temperature, humidity, wind information from different profiling instruments ready to be used for numerical weather prediction.
Great. Thanks, Carol, for that question. I had that very same question. Moving on to we have a couple more questions coming up, Hristo, so save your voice. This is a question from Austin Coleman. Hi, Hristo, really fantastic talk. Apologies if I missed this, but what impacts do you observe from area assimilation on ensemble spread statistics? The area experiment increased NEPs in the right places times, but do you notice changes in the fundamental nature of the bore among FCST members?
Thank you, Austin, for this question. Yes, ensemble spread, in this case, I know you've done a lot of work studying the optimal ensemble spread in forecasts for convective scale applications. I would say for my case, it is strongly force case. There was a lot of strong emphasis on the synoptic scale processes. That's one reason why there weren't terribly many discrepancies between the ensemble members when it comes to the simulation of the bore. However, one interesting fact that I didn't have time to show was that there were differences in terms of how the bores simulate explicitly the wave activity in their wakes. And so what I presented here were ensemble mean plots of the bores through my object-based algorithm that was able to recenter them such that the hydraulic jump is at the center of the cross-section. However, I did see variability when it gets to the simulation of these highly nonlinear wave processes that are happening in the subcritical region of the bore. So in that sense, there was variability, but perhaps in this case, it wasn't as much of an importance as to the mean state, right? So the moisture was very critical for increasing the amount of instability in front of the bores, but also the slight increase in the bore was systematically across many members. They had a lot of different representations of the wave activity, but on average, we did see this increase, which was ultimately what led to greater mechanical lifting along the bore structure. And that's why we did see this integrated, compounded increase in the neighborhood ensemble probabilities.
Great, thanks for that question. Our next question comes from Jürgen Jensen. Great talk, thanks. For a large number of photons, the Poisson distribution tends to a Gaussian distribution. How large must n photons be, and what does this correspond to in specific humidity? Is the Gaussian always a good approximation for MPD LiDARs?
Right, so this is interesting question, Jürgen, thanks for it. I like the Poisson distribution. The gamma distribution exhibits a similar property in that as we go further away from the bound, which is 0 in this case, we do see a convergence to a Gaussian distribution. So you're right in this case. I don't specifically know for the MPD instrument what the threshold would be for observing this convergence. However, this convergence is a little bit deceptive because by having more Gaussian distribution, it doesn't mean that the observing process becomes more linear. In fact, I believe Matt can confirm this, or other people working with the MPD instrument, that the more photon counts you have, I think the process becomes more nonlinear. So in that sense, a Gaussian model, which is typically based on a linear observation model, may not be the best choice here. So I would say Gaussian distributions are typically a good choice when we have quiescent conditions, when there is not much happening in the atmosphere, no phase changes, if we're not closer to bounds. But really when we start to see interesting weather, when we start to assimilate observations of these interesting weather phenomena, that's where we really have to think about non-Gaussian effects. And it's typically these interesting weather phenomena that would then introduce errors that will project onto the overall forecast errors. And we really need to suppress them to ensure that the practical predictability is also increased.
Thanks, Jürgen. Our next question comes from Matt Heyman. Your suggestion of assimilating using a Poisson model is very interesting. How flexible is DA with different noise models? We have recently found that sometimes photon counting is not Poisson distributed. Would we be able to modify the noise model to a modified Poisson distribution?
Thanks, Matt. Yes, Poisson model is one example. Craig's geeky NKF filter was another example in which we have gamma inverse gamma distributions and likelihoods to represent the observing process. And some of my future research, I hope we will be able to go in this direction of developing this adaptive likelihoods and priors, which are able to account for a set of different probability densities, not just the Poisson one, but for example, the Mueller distribution that you talked about a little bit, also anything relevant that could fit in this process. One complication here is mathematically, we perhaps have to think about what is a feasible set of distributions that can help us to modify the original equations. There are other ways which are non-parametric. So for example, the particle filter or the particle flow methods that have recently emerged in the data simulation community. These do not admit any specific density, so in that sense, they're more flexible. But right now, with the large dimension of the state, the large dimension of our problem, they're still not feasible. So this is an exciting area of research. Accommodating different distributions is exactly what I would like to do in the future, and I'll be happy to talk to you with respect to this problem. Thanks for the question.
Thanks, Matt. And the questions keep coming. You're very popular, Hristo. This is actually a comment from Dave Turner, a comment to your reply to Belay's question. The area retrievals assume that the humidity variable, mixing ratio, is Gaussian distribution at each height. So incorporating your idea on transforming that variable should help improve the retrieved product, at least a little bit.
Yes, that's I wasn't aware of the exact minimization optimization procedure for the error retrievals. I was more aware of the retrieval procedure for the MPD instrument, but that is very exciting, since if right now with these improvements that I was able to demonstrate in the second part of the talk, if you're able to modify and accommodate for the non-Gaussian character of moisture variables, then hopefully, at least theoretically, we should expect to see further forecast improvements. So thanks for this clarification, Dave.
Great, thanks. We have 4 questions on the list, and I know we're past the hour, but let's answer these 4 and then call it a day. This is a question from Craig Bishop. Often when model variable transformations are undone, the analysis ensemble variance no longer matches the analysis error variance. Have you come across much discussion or recognition of this in your investigations into assimilation methods of observations with non-Gaussian error distributions?
Thanks, Craig. That's a very relevant question, and I think this type of problem that you're alluding to here in your comment is perhaps some of the type of problems I would like to work on as I go into the future, because ultimately this nonlinear transformation approach that is naively being applied back and forth does not really modify the ensemble filtering equations. Rather, we're just having this ad hoc substitution of random variables, which seems to improve the analysis quality, However, we're not solving the Bayesian problem exactly. In fact, I have done some experiments with gamma inverse gamma type of distributions, which exactly fit the Geeky-NKF method. And I show that if I do a nonlinear transformation approach and follow this type of method, then the analysis solution is actually biased. Whereas if I do that type of approach for a log normal type of distributions, the nonlinear approach gives us an exact solution that has exact analysis spread as the posterior distribution. So we have certain distributions in which the spread and the mean and all other moments of the distributions are captured correctly, but we also have these other sets of distributions where we have problems we need to address. So that's the exciting area of research I would like to tackle on as I go forward. Thanks for the comment.
Thanks, Craig. We have a question from Jung-Kyun. Thank you for your great talk. 1, doesn't Profiler's wind observation have a rather negative effect on moisture analysis? And 2, the second part of his question, can your new non-Gaussian ENKF take into account physical relationships between photon and other meteorological variables?
Thanks, Jung-Kyun, for these 2 questions. On the first one, yes, the reason why the profiler had a negative impact on the moisture analysis was this inconsistency of what we observe and what we don't. So we only observe wind information, and in the case of the 6th of July case study, what the profiling instrument did was to increase the speed of the low-level jet. However, because we didn't have any information on the moisture, and because the cross-variable correlations in ENKF work in such a way that we simply extrapolate information to other parts of the state, it led to this deterioration of the analysis. We had a negative moisture bias in the control experiment, and really what the analysis should have done is to increase the moisture simultaneously with an increase in the wind variable. So two problems here: not enough observations. So the, let's say, the quote unquote observability of the system is not sufficient. And second, theoretically, perhaps these wind observations were not extrapolated in the optimal way to other portions of the state. On the second question, yes, the non-Gaussian method you're referring to here, for example, similar to Geeky-NKF for the EMPGF that I talked about earlier, it should account for the relationships between photon and other variables, but only in a local sense. Both of the methods are doing a non-Gaussian analysis with respect to the observed quantities, and then we still use a linear regression to extrapolate this information to other parts of the state. So it's a half-solved problem. There are other approaches which can be used to enhance the analysis quality. For example, we may want to use a nonlinear regression, similar to what Jeff Anderson has done in some of his previous work. So in this case, we'll be taking into account the nonlinear relationships between the variables, but we still need to be careful into understanding whether this solves the Bayesian problem in an optimal way. It could be a partial solution. Maybe we need more theoretical development, but it is one way to go forward.
Thank you. Thank you, Jung-Kyun. Thank you, Hristo. And we have one final question of this seminar before we close. This is from Tao Sun. Thanks for your great talk. I do not clearly get how you deal with the non-Gaussian problem. Do control variable transformation or assume the background error covariance under non-Gaussian distribution in the cost function? Thank you. Do you understand this question, Hristo?
I think I get the point here. So I think what she's trying to get at here is perhaps whether we still use nonlinear transformation in the new types of data simulation algorithm I was giving examples of. And these were just 2 examples of both in the variational world and the ensemble world. My point here was that we need to focus our attention on these type of methods going forward. There are no nonlinear transformation per se when we create these algorithms. The way that they're derived is we actually solve the Bayesian problem exactly. So suppose that you have a prior, which is log normally distributed. And suppose that you have a likelihood, which is also log normally distributed. Now, in order to find the posterior, what we do is to multiply these two densities together, and we arrive at a new function, which we wish to minimize. So this is how the Gaussian methods are derived. In the variational world, the way to do that is to take the negative logarithm of the resulting functional to arrive at a cost function. So we wouldn't end up with the same cost function as in the Gaussian case. This is the key. We change the analysis equations. We don't just do a nonlinear transformation. There may be nonlinear functions inside the cost function, but the form of the cost function is not the same as the original Gaussian-based cost function. And quite similarly with the ensemble-based methods, essentially the analysis equation represents a simple linear regression between the state and the observed variables. What I want to say here is that we actually have to derive new types of analysis solutions such that we stay away from this linear regression approach, and we actually derive a new set of equations in which we can rigorously incorporate different non-Gaussian distribution like Poisson, gamma, inverse gamma. This will change the form of the analysis equations, and they will become nonlinear. And that will create more difficulties in solving the problem. But this effort is worth doing because, as I justified in the two examples, it does improve upon the nonlinear transformation approach. Sometimes this would mean that we have to think about numerical implementations a little bit more carefully, but I think it's worth the effort, and we need to focus our future efforts in these type of new algorithms in which we stay away from the quadratic Gaussian-based analysis solutions. I hope this answers the query here.
Well, we are past the hour of our seminar. If you are interested in this research and have further questions, please reach out to Hristo via his email, which is provided on the seminar flyer. On behalf of EOL, M-Cubed, and CISL, I would like to thank the soon-to-be Dr. Chipilski for giving us the opportunity to hear about his work on assimilating ground-based remote sensing profilers and non-Gaussian methods. Thank you, everyone, and have a great day.
Thank you.